Vectors. A vector is a quantity having both magnitude, which is length, and direction. So geometrically, we can say that vectors are an equivalence class of directed line segments having the same magnitude and direction. An analogy is that 1/2 is the same thing as 2/4. Just a whole bunch of directed line segments. If they're the same magnitude and the same direction, they don't have to look exactly the same. We can see that we'll be able to move their positions. Analytically, this is an ordered pair of numbers. If this is vector v, I can think of this as being like from point A to point B. I can say vector b goes from point A to point B. I write that with a little arrow like this. Many textbooks will use bold notation for vectors. However, that's difficult to write in bold. We can label my vector with two parts. As the initial point, we sometimes call the tail, and the terminal point we may call the tip or the head. I want to point out that the order does matter. It is not okay that, say, this is vector BA, like this, because it starts from A and goes to B. You have to write it from A to B. Equal vectors. Two vectors are equal if they have the same magnitude and same direction. The zero vector can be written with 0 with a little bar above it or bold in a textbook. The length or the magnitude, same thing, is 0. This is the only vector with no specified direction. It has no specific direction. We may also say that it has every direction because it has no length, it's just a dot. So it can have every direction or no direction. I can combine vectors geometrically. I can do vector addition. If I have vectors u and v and I position them so that the initial point of v is at the terminal point of u, their sum is the vector from the initial point of u to the terminal point of v. So here's an example. So maybe this is vector u, this is vector v. Do we see that we have positioned the initial point of v at the terminal point of u right here? So their sum will be the vector from this point here to this terminal point of v, like this. This red vector is called the resultant vector. It is u plus v in this case. But you may also see the word resultant. You may refer to this as the triangle law. It may also be called the head-to-tail method. I may also use something called the parallelogram law to also show you how to add vectors. So let's suppose this is vector u, and maybe I have vector v. There's vector v right here. I line them up just like I did before with the head-to-tail method, but I also put another vector v at the beginning of u, from the initial point of u. Sometimes you can draw the other vector u here, and it would complete, right here in between, it would complete a parallelogram, but sometimes we just leave it like it is, and we say, well, this is the resultant vector u plus v. It's just like a triangle law. Just do the other two vectors. So this is actually the parallelogram law. We can talk about scalar multiplication. Remember that when we say scalar, we are talking about a real number. So if c is a scalar and v is a vector, then the scalar multiple c times v is a vector with length absolute value of c times the length of our vector v. If c is positive, the direction is the same as vector v. If c is negative, the direction is opposite of v. So if I draw two vectors, I can add them, multiply by a scalar, multiply by a positive scalar or a negative scalar. So let's suppose those are my two vectors, vector b and vector a, obviously given the two vectors above. I should say above. Find a plus b. 2a and negative 2b. For a plus b, I redraw a. Okay. Then I take b and put the terminal point of b at the initial point of a, like this. My resultant vector is right here, a plus b. To find 2a, I just draw the same vector in the same direction as a, then make it twice as long. So something like this would be 2a. For negative 2b, I double the length of b, but then I put the arrow in the other direction. So here's b, here would be another b, but now the arrow goes this way. So this is negative 2b. We say two non-zero vectors are parallel if they are scalar multiples of each other. One thing to keep in mind when you have two vectors that are parallel is they may have the same direction or the opposite direction. However, they may have completely different magnitudes. I can also find the difference of two vectors. Vector u minus vector v is the same as taking vector u and adding it to the negative of vector v. So using the same vectors I did before, just redraw them again. Okay, so suppose those are my vectors, vector b and vector a. If I want to find a minus 2b, let me keep in mind what negative 2b was. Let me do that first. And then I'm going to do my vector addition geometrically. Doing so, I end up with a minus 2b, this vector in red. Let's introduce a coordinate system. So I'm drawing my xy axes. Okay, so I can draw some vector in this picture. So this is vector a, and maybe this is a1, and this height is a2. So the vector has a terminal point at the point a1, comma a2. So I can say vector a equals, and I can use this neat component notation with this little triangle braces, a1, comma a2. That just tells me that if I start out at 0, 0, right here, I end up at the point a1, a2. And remember we said at the beginning that vectors are an equivalence class of directed line segments, so I could actually pick up this vector and put it somewhere else. I could pick it up here and draw it again as long as I have the same magnitude and the same direction. Vector A can be in any actual physical location. It just has to be pointing in the same direction and have the same length. So I put the tail of A at the origin, and the terminal point has coordinates A1 and A2. So I can write A using components. That's what I did up there. A equals the x component and the y component. And that tells me how far over to go. If I start at the initial point, I go over this many, a1 in the x direction, and up or down a2 in the y direction. A position vector is a vector that starts at the origin and has a terminal point somewhere else. So I can say vector A that goes from O to P, where O is like the origin, and ends at some point P. Maybe I can label it like I did before, A1, A2. It starts at the origin and the terminal point is at the point A1, A2. So if I have a vector going from point A to point B, where A has the coordinates x1, y1, and B has the coordinates x2, y2, then I can write vector A as x2 minus x1, comma, y2 minus y1. Here's an example. Find the vector represented by the directed line segment with initial point A, 0, 3, and terminal point B, 2, 3. So vector A, B, from A to B, I have to write it like this, equals, and I can just subtract the components. You always want to do final minus initial. So the final x-coordinate is 2 minus the initial was 0. The final y-coordinate was 3 minus the initial 3. We get 2, 0. Two things to find a vector, magnitude and direction. So what is magnitude? It's simply the length of a vector. So the length of A, it has written in component form as A1, A2 is A1 squared plus A2 squared all under a square root. We can think about why that would be true. I think about drawing my vector and then making a triangle out of it. If I want the length of the vector, the length is going to be right here. I can use the Pythagorean theorem, take this leg, A1 squared, plus A2 squared, and I get the hypotenuse squared. So that's how I find the magnitude. Algebraically, if A is equal to the vector A1, A2, and B is equal to the vector B1, B2, I can add them component-wise as A1 plus B1, comma, A2 plus B2. We talked about how to graph them geometrically. Now we just add the components if we're going to look at them algebraically. If I want to subtract, I just subtract their components. A1 minus B1, A2 minus B2. And if I want to multiply A by a scalar C, I just take C times my vector A1, A2, and that ends up being C, A1, and C, A2 as each individual component. Here's an example. If vector A is -3, -4, and vector B is 6, 2, by the magnitude of A plus B, 2A, and 3A plus 4B. So the magnitude of A, oh, and I want to point out one other thing. Magnitude is length. I didn't show you the notation. You may write magnitude of A like this with absolute value symbols. Some books write it like this with double absolute value symbols. They mean exactly the same thing. So if you see the magnitude of A and you're looking at this and your textbook uses double bars, exactly the same thing. So this means take the first component, square it, take the second component, square it, then take the root of both pieces. So we get what? The square root of 9 plus 16, which is the square root of 25, which is 5. So the magnitude of A is 5. And that should make sense geometrically. If I'm looking at vector A, 1, 2, 3, 1, 2, 3, 4, and this is the terminal point. The initial point is 0, 0. If I want to think about this as a right triangle, this is a 3, 4, 5 right triangle. Seems reasonable. If I want to find A plus B, I simply add the components. This is -3 plus 6 for the x, -4 plus 2 for the y, so I get 3 and -2. If I want to find 2 times vector A, I would do 2 times -3, -4, which is -6, -8. And if I want to find 3A plus 4B, I can do 3 times vector A plus 4 times vector B, which is what? -9, -12, plus 24 and 8. And then combining -9 plus 24, that's +15, and -12 plus 8 is 4.